Okay, 7.2 and 7.3 are a little bit tricky if you're just trying to follow along with the note. I purposely posted Mr. Todd's video as well. If you don't get mine, I would go watch his. We're obviously doing the same examples, but maybe just a different take on how to explain it. What I am going to say about these two lessons is I am not even going to come close to following what the lesson looks like on the note. I'm really just going to focus on the examples. In the note, they derive all the formulas, and it's quite, there's ants in my, it's a little bit tricky, and I don't want you to get totally focused on that. So what I will say, they have a derivation of the formulas and have them all printed. I would say in reality, don't even really look at it. What you need 100% is this trig identity toolbox. So this toolbox has all the trig identities that we need. And you might be saying to yourself, I thought we were skipping trig identities. Well, we're skipping approving trig identities, but we still need to use all the addition, subtraction identities and the double angle formulas in the next 2 units or 2 lessons. So they're super important. It will transfer over to calculus for anyone who's coming back or anyone who might be taking calculus in first year of university. So take the time to learn it. And I know I'm speaking basically to the last 6 people that are watching these videos, but for you guys, it'll be worth the effort you're putting in, 100%, especially if you're in grade 11 or if you're coming back. I can see how often everyone goes online, what they're opening, what they're doing, and the numbers are terrible. So for those people, I mean, their math future is their math future. Maybe they don't need it. I mean, I'm not personally offended, but okay. So what we really want to focus on, if you're going to take something out right now, is it says, it's the last 2 pages of the note that say awesome compound angle formula problems. Okay, so Mr. Todd came up with these problems. Basically, we're going to go through 7 examples that are very similar to homework questions that will really gear us towards exactly what we want. What is important is that you keep these formulas in front of you all the time, and you keep the special triangles in front of you all the time. So this toolbox, if on the back you want to write the special triangles in both degrees and radians, you want to put the cast rule, you want to put a bunch of that stuff, then that, if you carry that around with you every time you're doing your homework, it'll make it quite a bit easier. So the addition and subtraction formulas look like this. Basically, you're taking the idea of what happens with sine, cosine, and tangent if you're adding or subtracting 2 angles. Okay, how can you split that up? So there's multiple reasons we want to look at addition and subtraction formulas that we'll see throughout these examples. But the idea is they can all be written in a different way. And maybe you say, well, sine x plus y doesn't look that complicated, but this does. And maybe it is, but maybe you're going to go from something that's more complicated and try to get something that's a little less complicated. So I'm going to leave these up for the duration of the note. There are 2 sine formulas, 1 addition, 1 subtraction, 2 cosine formulas, 1 addition, 1 subtraction, and 2 tangent formulas, 1 addition and 1 subtraction. And they all have sort of different endings, but very similar. So the only difference between the sine ones is one gets a positive, one gets a negative. In cosine, it's opposite. The addition formula actually subtracts. 2 cosines, 2 sines. Here it was sine and cosine together. The subtraction formula actually adds. And the only difference here, the addition formula adds on the top, subtracts on the bottom. Subtraction, subtraction on the top, adds on the bottom. Now, you don't need to memorize these. And you didn't need to memorize them even when you were taking the course. If we weren't online, you would always be allowed to have this toolbox with you. So these are the ones we're looking at right here, the ones in the lower left. I'm going to keep them up here so that every question I do, I can reference them. Okay, so we'll start. It doesn't start off slow either. It starts pretty good. So what basically has to happen is this question says, rewrite sine 3x cos 5x minus cos 3x sine 5x as a single trig ratio. Okay, so we just want it to say sine of something or cos of something. A single ratio. We don't want it to be an addition or a subtraction. What you have to do is kind of look at this and see which one does this look most like. And you might not be able to go left to right. You might be able to go, you might have to go right to left, which is what's happening here. This is the complicated side. So we're looking for a sine and a cos together, a subtraction, and then a cos and a sine. So I personally did this in purple to make us look at the purple one. A sine and a cos together, a subtraction, and then a cos and a sine. So we know it's going to come back to equal sine of x minus y. The question is, what is our x and what is our y? So sometimes we kind of write it instead of with x's and y's, you might write it with a's and b's. Okay, so if I had written this, sine of a minus b equals sine of a cos of b minus cos of a sine of b, then this one would be much easier to identify, because when you looked here, you would say, well, in my case, my a is 3x, and my b is 5x. So when you wanted to get the actual answer, you could just go, well, sine of a minus b is sine of 3x, which is my a, minus 5x, which is my b. And altogether, this is equivalent to sine of negative 2x, right? 3x minus 5x is negative 2x. This is a single trig ratio. Okay, so that's what you are looking for, a single trigonometric ratio. Okay, when you get a single trigonometric ratio, it'll always be written in terms of one angle. Is the x still there? Yes. Could we help that? No. This was written in terms of x's. So the key here is you just want to use this and try to identify which one does it closely match to, and then work backwards, so you're working from right to left. Okay. The next one, it says we now have instead of having x's, we have actual angles, and they're in degrees to begin with, so that we can kind of start this off. Rewrite cosine of 75, cosine 15, plus sine 75, sine 15 as a single trig ratio. Then evaluate. So there's two parts of this. So again, you're going to look on the right side of all these and find out which one has two cosines and then two sines with an addition in between. So that's kind of the key here, is this addition. So two cosines and two sines are one of the cosine formulas. The one that has addition is this one. Okay, so we're really looking at this cos 75, cos 15, plus sine 75, sine 15 is going to equal cos of x minus y. We just have to decide what is our x minus y. Well, notice this would be cos x, cos y. So if you wrote it sort of underneath, just so we can see what it looks like, cos x, cos y, plus sine x, sine y equals cos x minus y. That's the original formula if I write it right to left. So really, when we compare to this one, it's easy to see that our x value is 75 and our y value is 15. So when we put them up here, we have an x value of 75, a y value of 15. So this whole thing can therefore be rewritten as a single trigonometric ratio of cos of, what is 75 minus 15? Cos of 60. Okay, so that is writing as a single trig ratio. We then want to evaluate it, which means you need to know what is cosine of 60 degrees, and not to a decimal, an exact answer, which means you have to use special triangles. Well, cosine of 60 is adjacent over hypotenuse, so it's 1 over root, oh wait, did I do something wrong? Oh, sorry, adjacent over hypotenuse, which is 1 over 2. Sorry, I did tangent. Cosine of 60 adjacent over hypotenuse, 1 over 2. So that would be the exact answer when you evaluate it. Okay, so it's a matter of, it's going to take some practice, but you're going to just keep referencing this little part of the chart and then seeing where it mixes in. Okay, it's going to get much more complicated. So we will go on to 3 and 4. So what I want to do, this whiteboard is going to get very filled in with information here, because I need to keep my special triangles up there. I need to keep all my addition and subtraction formulas up there. Okay, but slow but sure we will get this done. Okay, I'm no longer color coordinating. I'm not sure what's going to happen, so I'm just picking a random color to use. Okay, determine the exact value of sine of 105. Okay, so in the past, if we had a question like this, we would have tried to find a related acute angle for this and then use special triangles. The problem here is if I try to draw this in the idea that I draw the Cartesian plane, I draw 105 degrees. Well, 105 degrees is 15 past 90 degrees. Well, 15 degrees or 75 degrees is not a special triangle. Okay, so we can't actually find the exact value of this by straight using special triangles. But what you want to do is try to break up the 105, making an addition that uses some of the special triangle angles. So we're looking for things that are either 45s, 30s, or 60s. So basically, what two numbers out of 45, 30, and 60 could we use to make 105 degrees? Well, it doesn't take too long before you go, oh, I see. If I use 45 degrees and I use 60 degrees, then that adds up to 105. So basically, I'm breaking a single trig ratio into the addition of two other ones. Okay, which looks a little bit complicated, but really isn't. Okay, you just have to break down the angle into two that come from the special triangles. Then what you do is you apply the addition formula for sine. So I go up and I say, what is the addition formula for sine? Sine of x plus y, in this case my x is 45 and my y is 60, is going to be equivalent to sine of x, which is 45, cosine of y, which is 60, plus cosine of x, which is 45, sine of y, which is 60. Okay, so you've taken this addition formula and moved it into its longer version. But the longer version actually allows you to use the special triangles and to solve. So you go, okay, I can figure this out. I want to find the exact. The key of this is the word exact. I want to find the exact answer. I got to reference my special triangles and find them all. So I have to go, what is sine 45? Sine of 45 is 1 over root 2. This is all grade 11 work. What is cosine of 60? Cosine of 60 is 1 over 2. These two things are being multiplied. That's why I put the brackets there. Plus cosine of 45, which is also 1 over root 2. Sine of 60, which is opposite over hypotenuse, is going to be root 3 over 2. So when I actually multiply these, I get 1 over 2 root 2 plus root 3 over 2 root 2. Okay? So it's getting very close to looking nice. It does break some rules because it's got a radical in the denominator. We don't like that. It already has a common denominator, which is good. So really the only thing we're left to do is get rid of that root 2 in the bottom. You'll remember something called rationalizing. So you multiply both the top and the bottom by root 2. When I distribute this in, I get 1 times root 2, which is root 2. Root 3 times root 2, which is root 6. And then on the bottom here, root 2 times root 2 is just 2. Multiply that by 2 and you get 4. Okay? So the only real trick to this one, 2 steps that are new to grade 12. Splitting 105 into the addition or the subtraction of anything to do with 45, 30, or 60. That's the first step. Then applying the addition formula. Once you get it to here, from this stage on, it's a grade 11 question. Okay, especially if you leave degrees and it's super grade 11 question. Okay, we haven't even moved to radians yet, so just be aware that that is in fact basically a grade 11 question other than the application of this addition formula. Okay. If I was in class, I'd say so far so good. I feel like I still want to say that. Okay, we're going to move on to radians now. Radians is going to get slightly more difficult. It's actually going to amp up in difficulty quite a bit going into question 4. So question 4. Okay, question 4 has us doing what? Determine the exact value of sine 13 pi over 12. Well, basically the first thing I want to do is figure out what these special triangles are, but in terms of radians, because I know I'm going to have to use it in radians. Again, I said in the last lesson, If you're uncomfortable using radians, because we're learning online, you can replace the pi with 180 degrees and switch it into degrees. Do the question in degrees, and then the last step you'll have to convert it back to radians. If it's in radians, you have to answer it in radians for the most part, depending on how the question's set up. But what I want to do is just replace, we're still going to take these same triangles. I'm going to leave everything in the exact same position, 1, 1, root 2. 1, 2, root 3. But what I want to really analyze here is what angles are going to go in here. So these are 45 degrees. 45 degrees as a radian angle is pi over 4. So both of these angles are pi over 4. So just be aware, you have to think of that. And then in terms of 30 degrees and 60 degrees, 30 degrees, which is right here, is pi by 6. And 60 degrees, which is right here, is pi by 3. So I would suggest, again, obviously when you write this on paper, you have something a little thinner than a marker. You can actually put the angles in there. But these special triangles are going to be more important than the ones in terms of degrees. So you'll have to be aware that that's exactly what that special triangle looks like. And those are the ones you're going to use when you do a question like number 4. Okay, so have those set up, draw them out. Maybe you have to print this toolbox. If you don't have this toolbox printed, go print it now. And then start writing the special triangles on the back so that all in one piece of paper you have everything that's important. Okay, so the question is going to look like this. How do I start sine of 13 pi by 12? You're saying, I don't even know what 13 pi by 12 means. Well, let's take a look at that for a second. To me, the easiest thing to do is kind of look at where the whole pi is. So if I had 12 pi over 12, that would be pi. And we know this goes from 0, pi by 2, pi, 3 pi by 2. So if I go 12 pi over 12, then that gets me to here, and I just have to go one more pi over 12 over. So I know this is pi by 12. Okay, so basically I'm going all the way around here. So you're saying to yourself, okay, well, that gives me a related acute angle of pi by 12. So if this was yesterday, we'd say, okay, this is equivalent to, and if I look at the cast rule, I can see the only thing positive down here in quadrant 3 is tangent. So I automatically know my related acute angle is negative, and my related acute angle is pi by 12. Okay, so I have changed this slightly. I've changed it from 13 pi over 12 to pi by 12, which is much better. Okay, and now we want to do exactly what we did in the last question. In the last question we said, oh, we have 105 degrees. What two angles add up to 105? And we said, oh, 60 and 45, no problem. Now we just have to decide what two angles add up to pi by 12, because what we want to do is change this to some sort of addition or subtraction. Okay, so we're trying to make this into an addition or subtraction formula in terms of sign. Don't worry about the negative up front, that's not going to bother us. But we need to figure out what two angles, when we add or subtract, give us pi by 12. Well, the problem is none of these are in terms of 12 right now. So what I want to do is just somewhere on the side here, I'm going to write down what every angle that we have written here, pi by 4, pi by 6, pi by 3. Those are the three we get to work with. Okay, and because we are working with these angles, those are the only ones we can use to add or subtract to get us pi by 12, I want to get them to a denominator of 12. Who is it? Morgan? Are you coming in? Morgan, are you coming in?
Yeah.
Can you fit?
Yeah. I can.
Okay, so if I want to change this to something over 12, obviously I multiply the 4 by 3. I have to multiply the pi by 3. So this is 3 pi over 12. Okay, that shouldn't be hard for people to see. Pi by 6 is equivalent to 2 pi over 12. Pi by 3 is equivalent to 4 pi over 12. And now it's quite a bit easier to see how can I add or subtract these values to get a single pi over 12. And there's actually two choices you can do. Okay? you could take 3 pi by 12 and subtract 2 pi by 12. That'll give you pi over 12. Or you could take 4 pi over 12 and subtract 3 pi over 12. And that'll give you pi over 12. It doesn't matter. Okay, the one I happened to do when I did it was 4 pi by 12 minus 3 pi by 12. So I'll show you that one just so that it's consistent. I believe if you watch Mr. Todd's video, he did 3 pi by 12 minus 2 pi by 12. You're going to get the same answer regardless of what you do. You want to come say hi?
Hi.
Hi, Tutu. How do you like staying home?
Good.
Good? Are you going to do schoolwork today? Maybe? Okay, I gotta get on my way, Morgan. This is a long note. Okay, so what happens here is I now have set up the subtraction formula for sine. So I have to go up, that's the one in purple, the subtraction formula for sine.
It's a fine ant, I think.
Okay, just leave Morgan. I'm gonna leave the negative out front because that doesn't affect us. But when I apply this, just realize my x is 4 pi by 12. My y is 3 pi by 12. Okay? Now I'm going to convert it back actually just to make our lives easier. 4 pi by 12 was pi over 3. 3 pi over 12 was pi over 4. So I'm just going to do that because when we actually go to use the special triangles, they're not in terms of 12, so we might as well just convert that. So I need to change this subtraction formula, which again is the one in purple, and apply it here. So I'm going to have sine of what my x was, which was pi over 3, cosine of my y, which is pi over 4, and then I have to subtract cosine of my x, sine of my y. Okay, so there is quite a bit of calculations here. But again, you have the special triangles and you now have them in terms of radians. It's not so difficult. So we leave the negative out here. Sine of pi by 3. Here's pi by 3. Sine is opposite over hypotenuse, root 3 over 2.
I remember the pi by.
You remember the pi by?
Yeah.
Cosine of pi by 4. Cosine, anything pi by 4 is going to be 1 over root 2. Subtract cosine of pi by 3, which is 1/2. And this is 1 over root 2. So again, I'm going to leave the negative out front still. I get root 3. Morgan, don't push me, please.
I'm cold.
Over 2 root 2. Minus 1 over 2 root 2. Okay, and if I apply this obviously has a common denominator already of 2 root 2. And if I bring the negative in, negative times root 3 is negative root 3. Negative times negative 1 is positive 1. So I'm left with that, and the very last thing you have to do is simply rationalize. So you're going to multiply both the top and the bottom by root 2, and then you get a final answer of negative root 6 plus root 2 over 4. Okay? So it's a little tricky, but purposefully embedded in the note, a question that makes you think a little bit. You have to think about first, what is the related acute angle? Okay, you have to get it into a mode where you have a related acute angle. If you have an obtuse angle like this, you have to put it back into an acute angle. Then you have to think, how can I make this angle through an addition or a subtraction? Using only 45 degrees, 30 degrees, 60 degrees. Pi by 4, pi by 3, pi by 6. If the denominator here is in terms of something else, then change them all so you can see it easily. Okay? Maybe take a screenshot of this question, put it somewhere nice. You know you're going to get asked a question similar to this because it's so all-encompassing. Can you what? No, you can't take a screenshot because I don't want you to mess up anything. Okay, so we're already done 4 of the examples, so we're going to move right on to 5, 6, and 7, in which case I do not need the special triangles right now. So I'm going to erase everything below. Okay.
How many more minutes?
How many more minutes? Like 10. And then I have one more video after this.
I thought this is your second
No,
video.
this is my first. It's a long one, Morgan. Okay. So number 5, looks like this. And not too bad. Use the appropriate compound angle formula, so that means addition or subtraction formula, to find the exact value of sine
0.9.
2 pi minus pi by 6. Okay, so that's the question they're asking us. So basically here, all we're doing is just applying the formula. So we look, and it's again the purple one. Moving from left to right, so it shouldn't be that difficult. In this case, our x is 2 pi, our y is pi by 6, if you want to write that so that you know. So then when you apply the formula, you have sine of x, sine of 2 pi, cosine pi by 6, minus cosine of 2 pi, and sine of pi by 6.
Why are you in my house?
Okay. So then, you may want to say to yourself, well, why did you erase the special triangles? Aren't we going to need the special triangles? We could use the special triangles, or the fact that this is 2 pi, why do you want to come up with a related acute angle when we know so much about what sine and cosine look like? If you think for a moment about the two graphs, okay, so if you look at sine, it looks like this. This is pi by 2, this is pi, 3 pi by 2, 2 pi. Okay, so this is sine. If you look at cosine, which starts at 1 and goes like this, we're going to, this is pi by 2, pi, 3 pi by 2, 2 pi. Then you can already tell a lot about this question, namely where the zeros are or the ones are. So sine of 2 pi, what is sine of 2 pi? Well, where does it land? Exactly at 0. So all of a sudden I know, well, this equals 0. Do I even care what cosine of pi by 6 is going to be? No, why do I need to identify it? 0 times anything is 0. I don't even have to look up what cosine of pi by 6 is. Okay? If I want to look up cosine of 2 pi, I look at the cosine graph. What is cosine at 2 pi? Remember, this is fluctuating between 1 and negative 1. So cosine of 2 pi is just 1 times sine of pi by 6. So now, yes, you do need to know what sine of pi by 6 is. If you go back to the previous note and you look up sine of pi by 6, you will see that it is just 1/2. Okay, so now you get an answer of negative 1/2 for this question. So you don't, sometimes you have to use special triangles when it's pi by 4, pi by 6, or pi by 3. But if it's pi, or 3 pi by 2, or 2 pi, you can just use what the trig function looks like graphically. And that makes your life a little bit easier there. Okay, good? Okay, the next one, similar in manner. But in this one, they're not all angles. There's an x still involved. So it says, number 6 says, use appropriate compound angle formula to create equivalent expression to cosine of pi by 2 plus x. Okay, so the difference between 5 and 6 is now this one has an x. Again, you're going to use one of the formulas. So we look here, the one in light blue is the addition formula for cosine. So this is equivalent to cosine of x, which in our case is pi by 2, our first one. Cosine of y, which in this case is just x. Seems a little bit confusing. Minus sine of our first term, which is pi by 2. Cosine, oh, sine again. Sine of our second term, which is x. Okay, so all we need to know here basically is what is cosine of pi by 2 and what is sine of pi by 2, and that will answer our question for us. So when you go back, and again, I shouldn't have erased them, but sine pi by 2 is right here. Of pi by 2 is going to be a 1. Cosine of pi by 2 is right here. So cosine of pi by 2 is going to be 0. Okay, so in this case, again, you get 0 times cos of x minus 1 times sine of x. Well, 0 times anything is 0, so you really get a final answer, which is just negative sine x. Now, we did this question in 7.1 a completely different way. So be aware, you could have done it using all those, you know, we rotated to find related acute angle. The idea that you said, okay, well, pi by 2 is here, x is here. So this is pi by 2 over x. Then we found a related acute angle in there. That's how we did in 7.1. Now you have a new method using these angle formulas, which is much more straightforward. Okay, you still get the same answer either way, but it makes your life a little bit easier. Okay, Morgan, one more example. Okay, number 7. And number 7 is going to introduce two triangles that are in and of their own right, sort of special triangles, I guess you would say. What they are called is basically exact triangles, and there's two exact triangles that you're going to use quite a bit in this course. So I would also add these to your page. And the two exact triangles that you're going to use quite a bit, and by exact I mean we have full, one is called the 3, 4, 5 triangle, where these are exact values. That means they're not decimal, they're not rounded in any way. This is an exact proportionate triangle where you have leg lengths of 3 and 4, and you have a hypotenuse of exactly 5. So that's one of the exact triangles. The other exact triangle is a little bit funnier looking, is called the 5, 12, 13 triangle.
Ben's coming.
Okay, and those are Morgan, and those are exact values as well. So when you look at something like that, just be aware. You guys have to be quiet for one more. Ben, just be quiet. I'm just on my last example, and then I can stop. Okay, just be quiet for a minute. So these exact triangles we're going to use not only in this lesson, but we're going to use them in the next lesson as well. So just be aware of their existence. I would write them down, and then you're sort of ready to go. So in number 7 it says, if cos x, we know this about cos x, is negative 3 over 5, between pi
By 6.
and 3 pi by 2, and we know that tan of y equals 5 over 12. So you're going to start seeing 3, 5, 5, 12. That's the reason I put these in. Between 0 and pi by 2. If we know these things, what we want to calculate is what exactly is sine of x plus y. That's the goal. Okay. So first of all, we have to analyze what both of these mean. The first one being here. Cosine of x is going to occur between pi and 3 pi by 2. So remember what these graphs look like. 0, pi by 2, pi, 3 pi by 2. So this is occurring between pi and 3 pi by 2. So it's somewhere over here. Okay, drop a perpendicular, 90 degrees. And what it's saying is cosine of x, so this is angle x. Cosine, you'll remember, is x over r. So our r is here 5, this is negative 3. Okay, so that we know. Now what we want to realize in this question is this is an exact triangle. So we know if we have a leg length of 3 and a hypotenuse of 5, leg length of 3 and a hypotenuse of 5, that the other angle must be, or the other side length must be a 4. And in fact, it's going to be a negative 4 because it's down in the negative part of the y-axis, right? Now, you could have also solved this a different way. You can use Pythagorean theorem if you want. But because you can recognize it as a 3, 4, 5 triangle, then maybe Pythagorean theorem isn't necessarily needed. Like, it's much easier. But if you want, you could just call this, I don't know, side A, and then solve it by doing a squared plus b squared equals c squared. You'll still get the same answer. So this is what we know about x. What we know about y, angle y has to occur between 0 and pi by 2. So it's somewhere here is angle y. Okay? And it says that tan of y, okay, so tangent is opposite over adjacent is 5 over 12. We recognize right away 5 and 12 are leg lengths. That means this hypotenuse must be 13. Okay, all of that is going to be necessary for us to solve this part. Because this part wants us to solve for sine of x plus y. We go up to the very first formula and we say, okay, sine of x plus y is sine of x cos of y. plus cos of x sine of y. And now it's just a matter of actually plugging in what we know. What is sine of angle x? Well, sine of angle x is y over r, or opposite over hypotenuse, it's -4/5. Cos of y, we go to the y over here, cos is adjacent over hypotenuse, or cos, yeah, adjacent over hypotenuse, 12/13. Cos of x, we go back over here, cos of x, which was actually given in the question, -3/5. Sine of y,
Mommy, it's a stink bug.
cares. Sine of y, be quiet for a second, is opposite over hypotenuse, 5/13. Then when we multiply these all together, we get -48 over 50/65 minus 15/65 for a final answer of -63/65. Okay? So it's sort of a matter of, you have to look at the restrictions of what part of the axis it's in, because that's going to tell you whether the values are negative or positive. So that's somewhat important. And then draw it out, and then if it's not an exact triangle, then you'll have to use Pythagorean theorem to find the unknown side, depending on what ratio is given. Okay, I think with these 7 examples, you have a pretty good shot at doing the 7.2 homework. If you want to go back and look at how the formulas are derived, you can, but that is not a requirement of this course at this time. Okay, I'm not going to ask you to derive any formulas on the assignment. Okay, good. Feel better about that.